Hey, I just wanted to quickly plug that if you guys want any tutoring, some new slots have opened. If you look in the description, there's a link to my physics and maths tutor profile in which I do tutoring on there. Okay, so coconut oil contains a triester with three identical R groups. This triester reacts with potassium hydroxide. So what we're dealing with here is an example of an oil. The same thing applies to fats. So how these form is that you've got esters of glycerol and fatty acids. So what glycerol structure is you've got C, 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 H, 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 OH, OH, and OH. This is glycerol, also known as propane 1, 2, 3 triol. Now, when you're forming an ester bond, what happens is you've got this condensation reaction, a molecule of water is released, and you're reacting it with a carboxylic acid. So when you're reacting an alcohol group with a carboxylic acid, you end up having an ester. So the group you're looking for in esters is this C double bond O O C. This bit here is your ester link. Now, the relevance of that here is that you can see there's that link here. You've got that COO there. That's going to be a C double bond OO. And you've got three carbons here. So this is your glycerol part, and these are your fatty acids joined together by ester. With esters, you can do something called base hydrolysis, which is where you use sodium hydroxide or potassium hydroxide. The OH minus from the sodium or potassium hydroxide reacts with the fat or oil, and it forms a carboxylate ion and an alcohol. So the carboxylate ion is basically the acid part without the H. So for example, if I had this made up acid, if I had this acid here, like this, its carboxylate ion would be this. It's lost that H plus. So that's what we've got on here. So these are the fatty acids. You can see that you've got your carboxylate ions here with a K on it because it's reacted with the potassium. So what the other thing has to be is it's got to be the rest of this oil, which has to be glycerol. So the other product here is going to be C, 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 OH, 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 H, 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 like so. Name the type of the compound shown by the formula RCOOK and then give one use for it. So this is a carboxylate salt. So it's that carboxylate group that's reacted with the potassium, giving you a carboxylate salt, and the use is that you can use it in soap. The triester in coconut oil has a relative molecular mass MR of 638. In the equation shown at the start of question 1, R represents an alkyl group that can be written as CH3CH2N. Deduce the value of N in CH3CH2N and show your working. So what this question is telling you is that this whole thing equals 638, and this R bit here is some multiple of CH3CH2N. So what I'm going to do is I'm going to work out the MR of what we already know. So we know that we've got 3 carbons here, so that's going to be 3 lots of 12, plus 5 hydrogens here, so that's going to be 5 lots of 1, plus 3 lots of, because there's 3 of these COOs, 3 lots of 12 plus 16 plus 16. If I work that out, I get 173. That means whatever's left over has to be the R groups because we didn't count those initially. So this means that 638 minus 173 is those 3 R's left. That's the only thing that we haven't calculated. So if we do that, 638 minus 173, we get 465. So that equals 3 of these R groups. We want to work out one of them. So I'm going to divide this by 3. So 465 divided by 3 gives you 155. And that equals one of those R groups. So they've told us that each R group is a certain multiple of, so it's going to be CH3 plus a certain number of CH2Ns. So that means we're going to have the mass of CH3, which is 15, plus N lots of the mass of CH2, 14, and that equals 155. So therefore, N lots of 14 equals 155 minus 15, which is 140, so N equals 10. And that's how you get it. A 1.450 gram sample of coconut oil is heated with 0.421 grams of potassium hydroxide and aqueous ethanol until all the triester is hydrolyzed. The mixture is cooled, and the remaining KOH is neutralized by exactly 15.65 centimeters cubed of 0.1 mole per deciliter cubed HCl. Calculate the percentage by mass of the triester in the coconut oil. Okay, so before we get started, we need to write out a basic overall equation. So I'm just going to write in words just so I get my bearings right. So coconut oil plus 3 moles of KOH gives you, your products, whatever, right? So they've told you that we've heated it with this much KOH. So the moles of KOH at the start is going to equal 0.421 divided by its MR, which is going to be 56.1 if you work out using a periodic table. If you do that, you get 0.421 divided by 56.1 gives you 7.504 times 10 to the minus 3 moles. Now, some amount of this will have reacted with the coconut oil, and what they did is they took the rest of it and reacted it with HCl. So, just as a reminder, the reaction between KOH and HCl is going to be KOH plus HCl gives you KCl plus H2O. They react in a 1-to-1 ratio. So we can work out the moles of HCl used, which is going to be its concentration times its volume, so 0.1 times 15.65 over 1,000, which gives you 0.1 times 15.65 over 1,000, which gives you 1.565 times 10 to the minus 3 moles. So that means whatever was left over must have been this amount because it was reacted exactly because they're in a 1-to-1 ratio. So that means the moles of KOH at the end, after you've done the hydrolysis part, is going to equal 1.565 times 10 to the minus 3 moles. Therefore, you can go backwards and work out how much actually reacted with the coconut oil. So the moles of KOH reacting with the coconut oil is going to equal the total number of moles we worked out at the absolute start, so 7.504 times 10 to the minus 3, minus the moles at the end that reacted with the HCl, which is going to be 1.565 times 10 to the minus 3. We do that, we get a nice old answer of 5.939 times 10 to the minus 3 moles. So now we know how much potassium hydroxide reacted with the coconut oil. So we can work out how many moles of coconut oil we have as well. So the moles of coconut oil is going to be a third because they react in a 3-to-1 ratio. So it's going to be a third of that. So the moles of oil is going to be 1/3 times 5.939 times 10 to the minus 3, blah, 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 which equals 1.9797 times 10 to the minus 3 moles. You don't want to round too much until you reach the end. Now you know that mass equals moles times MR, which is going to be 1.9797 times 10 to the minus 3 times the MR of the coconut oil, which they've told you is 638. 638, and that gives us 1.263 grams. So we're nearly there. They want us to work out the percentage by mass of the triester in the coconut oil, and we had a 1.450 sample. So you do 1.263 divided by the total mass of whatever this stuff is, this coconut oily mixture stuff, 1.45 times it by 100. And you get a lovely answer of 87%. Suggest why aqueous ethanol is a suitable solvent when heating the coconut oil with KOH. Give a safety precaution when heating the mixture and justify your choice. So it's a suggest question where they want you to infer a conclusion. So it's not something specifically you need to know. It's more so you need to be able to draw a conclusion. So think about what we're reacting here. We've got coconut oil, which is a fat. It's a oil, sorry. Like a fat and oil slash thing. And you've got potassium hydroxide. Fats and oils are insoluble. Potassium hydroxide is soluble. So it's probably that they use aqueous ethanol so they can dissolve both of them. So it dissolves both oil and KOH. Now it says, give a safety precaution when heating the mixture. So you can't just say something like, wear gloves, tie hair back. Like that's stuff you do as standard, lab practice. You need to think about something that relates to heating the mixture. Now, in general, when you're heating organic chemicals, nearly all of them are flammable. So you don't want to put them near a naked flame. So instead, what we could do is we could use a water bath or a sand bath or an electrical heater. So use a water bath to heat the mixture. Why? Because it's to prevent the risk of fire. Pretty much everything in organic chemistry that you're going to handle is going to be, flammable. So this question is about fuels. The petrol fraction obtained from crude oil can be used as fuels in cars. State the meaning of fraction as used in the term petrol fraction. It basically just means a group of compounds that boil at a similar range of temperatures or have a similar boiling point. So group of hydrocarbons that boil at similar temperatures. Hexadecane can be cracked at high temperatures to form petrol. Complete the equation to show the cracking of one molecule of hexadecane to form hexane and cyclopentane only. Give the name of the catalyst used in this reaction. So we're making hexane. So hexane CnH2n plus 2. So it's going to be C6H14. And then cyclopentane. So cycloalkanes have the same general formula as alkenes. So CnH2n, not CnH2n plus 2. The reason being is because they're cyclic. So, because they join at each end, you lose two hydrogens. So in this case, the formula of cyclopentane is going to be C5H10. But we're not done here because this has to have split into all of these perfectly. So you need to work out how many of these add up to make this. So if you put 2 here, you've got 10 carbons and you've got 20 hydrogens here, and then you've got 6 carbons. 10 plus 6 is 16, that gives you C16. And then 14 plus 20 gives you 34, so that balances out. And the catalyst for this is zeolite. So carbon dioxide is formed when a petrol is burned. Carbon dioxide acts as a greenhouse gas when it absorbs infrared radiation. Give a reason why carbon dioxide absorbs infrared radiation. So this is taking what you know about infrared spectroscopy. How infrared spectroscopy normally works is that IR radiation, so infrared radiation, is absorbed by covalent bonds in the molecules. So those bonds are always vibrating at different frequencies. So they're vibrating at a different number of vibrations per second. If the IR radiation has the same frequency as the bonds, it is absorbed. So what's going on here is that the C double bond O bonds in carbon dioxide vibrate at the same frequency as IR radiation. So how they use IR spectroscopy is they vary the IR radiation's frequency. If they change the frequency, then obviously, like I said, different bonds vibrate at different speeds and they absorb different amounts of IR. So they can look at how much IR is absorbed and then work out what the thing probably was. So that's how IR radiation works, and that's how you apply to this question, is that C double bond O bonds in carbon dioxide probably vibrate at the same frequency, which is why they take it in. Compound Z, this can be used to remove carbon dioxide from a mixture of waste gases produced in some of the power stations. Figure 1 shows a part of a suggested mechanism for the reaction of Z with carbon dioxide. Now it says draw 2 curly arrows to complete the mechanism, name compound Z, and then deduce the role of Z in step 2. So although the mechanism isn't entirely crystal clear here, as long as you have a decent understanding about how all of them work, then you should be okay. So you can see here that we've got this nitrogen here, this amine group, this NH2, with a lone pair of electrons attacking this carbon, which is obviously going to be slightly positive because this oxygen's more negative, electronegative, so it's going to draw the electrons to that side. So it's acting as a nucleophile. So you can see that it donates the lone pair of electrons here, this bond breaks and the oxygen steals them electrons. So now you've got this negative oxygen here and you've got an N plus here. Now, in organic compounds, N only likes to be bound to 3 other things, but you can see there's 4 here. So what happens in the second step is that we need to basically break this bond down until we don't have, 4 things around this nitrogen. So the first thing that needs doing is we need to try and nab something. So what happens is the lone pair from another molecule here comes along and donates its electrons like that. This bond breaks with this nitrogen, and then you're left with the end product. This ammonia molecule donates the lone pair of electrons to the hydrogen to form a bond, and then this means the nitrogen over here no longer has a positive charge. However, now this one has an extra H plus as well. So now this forms HOCH2CH2NH3, and it's a plus because it's now stolen that extra H from that side. So you can see that's what we have here. And it's now reacted with HOCH2CH2NCOO minus. So now it says to name the compound Z. So the carbon chain 1, 2. So it's going to be ethan something. It's got an alcohol in, so it's going to be ethanol, and it's got an amine on the second carbon. So it's going to be 2-amino-ethanol. And what's it doing in step 2 of the mechanism? Well, what's happened is it's accepted a proton, so it acts as a base. So HOCH2CH2NH2 can be represented as XNH2, and HOCH2CH2NH3 plus can be represented as XNH3 plus. Draw the shape of XNH2 and of XNH3 plus, and state whether the H and N bond angle is greater than or less than the one in X and NH3 plus, and explain your answer. So whenever you want to find out the shape of a molecule, you need to know how many bonding pairs and lone pairs there are. So you need to figure out how many of those types of bonds there are around the central atom. So the central atom in this case is going to be N, and in this case we've got NH2. So that means sorry, X and H2. So we've got an X bonded to it, and we've got an H bonded to it, and another H bonded to it. Now, nitrogen's in group 5, so it's 5 outer electrons. So if it's got shared pairs with all of these, it's got 2 extra lones left, like so. Whereas if you've got XNH3 plus, you've now got 4 bonding pairs, 0 lone pairs. So you've got 3 bonding pairs, 1 lone pair here. And now you've got 4 bonding pairs, no lone pairs. So you end up with H, N, H, H, X. So make sure you draw them 3-dimensionally. And also this is a plus as well. It's got a charge, so you have to write the whole thing like this. Now it says state whether the H and H bond angle is greater than or the same than or smaller than. Remember that lone pairs, so out of the repelling, you've got lone pair and lone, they repel the most, and then you've got lone bonding, and then you've got bonding. Okay? So in this case, we have a lone pair, we've got bonding. And here we've got bonding. So this one's going to have a bit more repulsion because we have a lone pair here. So the angle is actually going to be smaller. The reason is because lone pairs repel more than bonding pairs. And if you think about it, this is 3 bonding pairs, 1 lone pair. So this is going to be trigonal pyramidal. The angle is 107 degrees. Whereas in this, you've got 4 bonding pairs, 0 lone pairs. So this is going to be tetrahedral, and the angle is 109.5 degrees. Bioethanol is used as an alternative for fossil fuels. This statement appeared on a website. The fact that bioethanol is a carbon-neutral fuel outweighs the environmental disadvantages of producing bioethanol. Evaluate this statement. In your answer, you should include an outline of how it's produced, relevant equations, and analysis of. Okay, so this question wants us to evaluate the statement, so we need to say what supports it and what doesn't support this statement. So let's talk about the processes leading to it. So when you're burning hydrocarbons, you're going to produce CO2. But plants take in CO2 and convert it to glucose, which can then be used to make more biofuel using like yeast or other things in the fermentation process. So we need to show how this could potentially be carbon neutral. So what happens is the first step is that plants use CO2 to photosynthesize. And then you need to write the equation. So the equation for this is 6CO2 plus 6H2O gives you C6H12O6 plus 6O2. So the next thought is that we take this glucose and then we convert it into ethanol. So when we do that, you're doing fermentation. So fermentation produces bioethanol using the glucose from photosynthesis. So the equation for this one is you get your C6H12O6 and you're making bioethanol. So it's going to be C2H5OH, C2H5OH plus 2CO2, and there's a 2 in front of that. Sorry, whoops. Right. Now, obviously, we actually need to make use of this. So we're going to burn it. So we combust ethanol. The equation for the combustion of ethanol is 2C2H5OH plus 6O2 goes to 4CO2 plus 6H2O. Now, obviously, if we combine these equations, you can see that 6 moles of CO2 are taken in and 6 moles are released. So you can see there's a 4 here and there's a 2 there, so that adds up to 6. So 6 CO2 taken in, 6 CO2 released, suggesting it is, a carbon neutral. Now, the issue is that, we need to talk about the other processes that can mess with this. So, for example, we need to use fossil fuels to actually harvest crops. There's also problems with actually getting hold of the crops and providing energy to actually do these processes. So it's not technically entirely carbon neutral because, for example, we still need to burn fossil fuels to provide energy, or heat energy, sorry, for fermentation. Not only that, we need to use fossil fuels as well to harvest crops. And these both release CO2. But that doesn't match with what we said here because we said that it's a perfect CO2 in, CO2 out. But these processes that are outside of this, you know, release CO2. So there's an imbalance. So therefore, it can't technically really truly be 100% carbon neutral for those reasons. As well as that, there's other things you could talk about. So, for example, you know, there's fuel used in like its distribution as well. So, like actually driving it from one place to the other. And as well as that, you're also destroying like, habitats and stuff. Okay, so a student does an experiment to determine the value of the enthalpy of combustion of heptane, and here's some of the apparatuses. You've got a burner, heptane, 100 grams of water, cup of blah, 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 whatever, right? So design a table to record all the readings necessary to determine an experimental value for the enthalpy of combustion of heptane in this experiment. So the formula you need to know of is Q equals mc delta T. So M is the mass of water heated, not the mass of fuel. C is your specific heat capacity, which is like 4.18 something something something, and this is your temperature change, and this is in joules. The issue with this, however, is that this only gives you the heat energy released. It doesn't give you the enthalpy change of combustion. The enthalpy change of combustion is where you have 1 mole of a substance completely combusted in oxygen in standard conditions, blah blah blah. So in this reaction, we don't have perfectly 1 mole of heptane, right? We might have 2, 3, 4, 5, 20 moles, however many moles. So the temperature change for this correlates to how many moles of heptane we have. So in order to get it to be the temperature change for 1 mole, you have to divide this by the moles of fuel used to get an answer in kilojoules per mole. That's your enthalpy change. This here, sorry, is just a heat energy change. This gives you the actual enthalpy change. So in order to construct this, we need a temperature in degrees Celsius. We need the initial temperature, the final temperature, and we also need the change in temperature as well, delta T. As well as that, we need masses. So we need mass, the gram. So we need burner before, burner after, and then the delta, like burn mass. Basically, how much we burned. Because then we know if we know how much mass of the heptane we burned, we can work out how many moles of heptane we burned. So, for example, if we worked out that there were 6 moles, and this gave us 60, joules as a calculation, I'm just making this up. That means 6 moles makes 60 joules of energy release. So therefore, 1 mole would be 10. That's a enthalpy change per mole. So it's very important that you appreciate that sort of definition and distinction. That's why those enthalpy change definitions are important. The student considered using a glass beaker on a tripod and a gauze instead of the clamped copper calorimeter. Suggests 2 disadvantages of using a glass beaker on a tripod and gauze. So, let's think about what's going on in this experiment. So you're burning something and you're hoping that all of this heat energy goes into the water and isn't lost into the environment. It's not gone somewhere else. It's not heating up the actual, copper calorimeter itself. If we use glass is a pretty bad conductor of heat. So we're just gonna lose a lot of the heat energy to the surroundings of the glass itself rather than getting into the water. This only works provided that all of the heat energy that was released from here goes here. So first of all, it's that glass is a worse heat conductor than copper. As well as that, if you think about it, if you've got a tripod and gauze, you've got something else in the way of the heat as well. So you've got even more blocking of the heat. So tripod and gauze reduce heat transfer. Suggest 2 reasons why the value of enthalpy change of combustion in this experiment is less exothermic than a data book value. The enthalpy change here that we're working out is working on the assumption that we're losing that heat energy from the burner to the water. So what they found is that the water has taken more of that heat energy in, but we found that it hasn't taken as much. So there's 2 reasons for this. One, like I said before, we're assuming that all of the heat's gone into the water. So one, we might have lost the heat to the surroundings. So some of it, might have gone off, dissipated somewhere else, or it might have actually gone into heating the actual calorimeter itself. Or the other thing is we just didn't burn it completely because the enthalpy of combustion requires that you combust something completely under standard conditions. So heat, energy, lost to surroundings, or we have incomplete combustion. So just one addition to this apparatus that would improve the accuracy of the enthalpy value obtained. I mean, probably just putting a lid on might help. Put a lid on. Other things you can talk about is using a windshield or insulating the sides of a calorimeter. All right, so Kekulé suggested this structure for benzene. So you've got 3 double bonds here and 6 carbons. Benzene is now represented by this structure with the ring, and it shows the relative stability of the ringed one compared to the Kekulé structure. So you can see that we have a little Born-Haber cycle going on here. So let's have a look what's going on here. So we've got 6 carbons solid plus 3 H2 gas, and we're forming benzene. So that has to be the enthalpy of formation because you're making 1 mole of a substance from its constituent elements in their standard states. We're making 1 mole of benzene from 6 carbons in its standard state solid and 3 hydrogen gases in their standard state H2 gas. So it's important you know your enthalpy definitions or it's game over. Okay, right. So we've got delta H2 is a mystery thing here. But if we look at this one here, so we're starting with the Kekulé structure and we're breaking it down into 6 carbons and 6 H's. So we've broken every single bond. We've done a bond enthalpy, which is where you break 1 mole of a bond, averaged over multiple compounds, blah, 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 under standard state. So it's again important you know your definitions. So just as a reminder, just to label it, delta HF here, and these are all your bond dissociation enthalpies. Okay, so now we're going from 6 carbon to 6 hydrogen gas. Okay, fine. Now, if we look here, we've got 6 carbon in its standard states, 3 H2 gas in its standard states. We have an arrow going upwards. So if we're going from 6 carbon to 6 gas, we're making gaseous atoms from 1 mole of a substance in its standard states, or 6 in this case, sorry. This is going to be enthalpy of atomization. And you can see here we've got 3H2 becoming 6H. So these are delta H atomization. So now we can work out the rest. This is based on the principle of Hess's law. So if you start at the same point and finish at the same point, the overall enthalpy of change is the same regardless of where you go. So the example I use is imagine this is your home, that's Tesco, and it's 1 mile away. If you go all the way to Australia and Tesco, you're still 1 mile away from your home. So how do we actually make sense of this? So let's say we start with our Kekulé structure. I'm going to label this one as well, delta H bond dissociation. Right? This arrow is going from benzene to the Kekulé structure. So what we can do is we can go around this right around the cycle, and you'll still start off at benzene and end up with the Kekulé structure. So that will equal the same as this. So if we follow that path, what we're doing is we're going opposite to delta H1. So it's going to be negative delta H1, right? And we're following this arrow, so it's going to be plus delta H atomization of everything, blah, blah, blah. We're going against this arrow, so it's going to be minus delta H bond dissociation enthalpy, right? And that will get us to here. So if because we're starting at benzene and ending up at the Kekulé structure, regardless of if we go this way, it's going to be the same as this way. So that means that that has to equal delta H2. That's how you use a Born-Haber cycle. So now we actually need to work out some of these bits and bobs. So they've told us that delta H1 is plus 83, but we're going the opposite way. So minus 83. Right. Now we need to work out the enthalpy of atomization is for all of these. So the enthalpy of atomization is going to be 6 lots of the one for carbon and 6 lots for the one for hydrogen, because the definition of enthalpy of atomization is making 1 mole of 1 mole of gaseous atoms from an element in its standard state. So it's not 3, it's going to be 6 because you're making 6 moles of it. So the enthalpy of atomization of carbon, all of that is going to be 6 lots of 715 plus the one for hydrogen, which is going to be 6 lots of 218. Right. Now we need to subtract all the bond dissociation enthalpies. We need to add them all up. So we're breaking every single bond we calculate, and then we go the opposite way to it. So that's going to be 3 lots of C double bond C, 3 lots of CCs, and then 6 lots of CH. So 3 C double bond Cs is going to be 3, 6, 1, 2, plus 3 lots of CC, so it's 3, 3, 4, 8, plus 6 lots of this, so that's going to be 6, 4, 1, 2. So now I'm going to tidy up everything by making everything look a bit nicer. I'm sorry, that all equals delta H2. Okay, so now we've written a really hideous thing, so let's tidy all of this up. So I'm going to add all of these together just to make it a bit tidier. So 83, sorry, minus 83 plus 6715 plus 6 lots of 218 gives you 5515, and then we're subtracting all of this stuff in the bracket. So 3 lots of 612 plus 3 lots of 348 plus 6 lots of 412, 5352, and that gives you delta H2. So that means delta H2 is just these two taken away from each other, which gives you a nice old answer of plus 163. Remember the plus, because if you say your enthalpy change, you need to clarify whether it's gone up or down. If I say my weight's changed, you don't know if it's gone up or if it's gone down. So as a quick summary, just to remind you on how I did this question in case that working out got a bit hefty, what you need to do is you need to identify all the enthalpy changes you can see here. So we're going from elements in their standard states, blah, 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 whatever, to forming benzene. So this is going to be delta HF, this one here. This is the mystery, enthalpy that they want us to solve. We don't know what it is because we don't know any definitions that match that. If we look at this line here, you can see that we're going from the calculate structure of benzene to atoms. So 6 carbons, 6 H's. So this has to be the bond dissociation enthalpies, right? Now, if we look at this arrow here, we're going from 6 carbon solid and 3 H2 gas to 6 carbon gas and 6 H gas. So this has to be delta H atomization of everything. So you need to work out basically all of the sums of each one of those, which I've done here in one big step. But you could do them separately and label them here and then use those. Because you're starting with benzene and you're going to calculate. So what if I did it this way, where I started at benzene, went all the way around this way, and got to calculate? It's the same thing as this because you're starting and ending at the same point. It says explain in terms of structural bonding why the new benzene structure is more thermodynamically stable than the calculated one. It is because the electrons are delocalized. Whoops, the pi orbital electrons are delocalized. Okay, so a mixture of concentrated nitric acid and concentrated sulfuric acid reacts with benzene. Figure 4 shows the incomplete mechanism of this, and it says name the mechanism and do all of these things, blah, 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 fine. So the mechanism by which we're doing this is electrophilic substitution. You're generating an electrophile, and then what you're doing is you're substituting one of the atoms on the benzene with NO2. So fine. Now, if we look at this step 1 here, we can see that we've got O2N08. So we've got HNO3 right here, right? And we've got H2SO4. Now, this O2N has got an O+. So what's happened is that this oxygen has nabbed a hydrogen. It says in step 1, we need to add 2 curly arrows. So what's happened is this oxygen's formed a bond with a hydrogen, which must have come from here. So we've got a lone pair of electrons from this oxygen, like this. Obviously, if it takes this H, then this bond has to break. So this bond breaks, and that gives you what you expect. You get your O- with the extra electron here, and you've got your oxygen with the plus. So that's that first bit done. Now it says in step 2 to add a singular curly arrow. So let's have a look what's going on here. So you've got O2N, which is bonded to O plus and HH, and then you end up with O2N on its own and OHH like this. So that means that this bond has broken. We need to decide which way does it go. Does it go this way or does it go this way? You can see that this is an O plus and now it ends as an O. So that means this bond has broken like this. This is your standard electrophilic substitution stuff. So the electron comes out of the pi like this and it goes like that. This ring breaks and then you've got an H and an N here. And then you need to draw another curly arrow going from the H to into this ring to feed it back in and restore the ring. And the H comes off when the bond breaks. So whenever you do these kinds of questions, the mechanisms aren't always going to be crystal clear. It's not going to be like some very standard mechanism. What you need to do is you need to compare before and after and see what's changed and see what's happened. So you can see here, for example, this O plus has become an O, so it's nabbed electrons from somewhere. And you can see this has become an O2N plus, so this has lost electrons. So this bond must have split in such a way that this O has nabbed the electrons, this has lost them. So if you do that, that helps a lot. Okay, this question is about equilibrium. 1 mole of a diester with this formula C7H12O4. So I'm going to highlight that it's a diester. This might be of use later. Is added to 1 mole of water in the presence of a small amount of catalyst, and the mixture is left to reach an equilibrium at a constant temperature. So we've got this ester becoming a carboxylic acid and an alcohol. At equilibrium X moles of ethanoic acid are present in the mixture. Complete table 2 by deducing the amount in terms of X of the diester, water, and diol present in the equilibrium mixture. So whenever you have an equilibrium question, it says this much of something was mixed with something else, and then at equilibrium, this is how much we have. You need to do this anyway. They've set it up for you. So at the start of the equilibrium's not actually had a chance to set itself up. So you've got 1 mole of your diester, and they've told you that they've added it to 1 mole, so you can have the same as the start. Because the equilibrium hasn't really done anything yet, you've got 0 of the acid and 0 of the diol. However, at equilibrium, we've now formed the acid, and the acid must have come from these two. So these two have to have dropped to produce X amount of this. The amount of diester, so if this is increased by X, then this must have dropped by, it must have fallen by half X, because this is a 2-to-1 ratio. You got 2 here and you got a 1. So that means if this has gone up by X, this has to have fallen by half X. So that means it's 1 minus X over 2. Now with water, they're in the same ratio 1-to-1. So if you made X of this means it has to have fallen by X. So that means it's going to be 1 minus X. And the amount of diol, again, 2-to-1 ratio. So this means this has gone up by X over 2. So it's going to be X over 2. So it's just really important you understand that concept. At equilibrium, if you have this much, that means that, this much in proportion to these is decreased. It says deduce the structure of the diester in question 05.1. Okay, right. So in ester, the interesting group here is that, so esters, the key part of an ester is you've got a C double bond O, O, C like this. You've got your carboxylic acid derivative here and your alcohol derivative here. Right. So I'm going to start off by doing basically each end of the ester. So I'm going to have C, C double bond O, O, C like this. And on the other end, I'm going to have C, C double bond O, O, C like this. And then it's just fill in the rest. So 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. Because we've got all 7 there. And you just add in the hydrogens. So 1, 2, 3, H, 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 H. And then just check it all adds up. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. That adds up. 1, 3, 5, 7, 9, 12. So there you go. That's how you do it. A new equilibrium mixture of the substances from question 0.51 is prepared at a different temperature. Table 3 shows the amount of each substance in this new equilibrium mixture, and the value of Kc is this. Calculate the amount of water. Fine. In moles. Cool beans. Cool. So Kc is going to equal the concentration of so CH3COOH squared times OH CH2 3OH, right? Because 2 1, and then it's going to be divided by C7H12O4 and then H2O squared. Okay, so what we need to do is we need to rearrange this. So I'm going to move this up here. I'm going to times both sides by H2O squared and then divide both sides by Kc. So that gives me H2O squared equals CH3COOH squared OH CH2 3OH all divided by C7H12O4 times Kc. Now you might be thinking, we're in a bit of a pickle because this uses concentrations. We've not been given a volume, so we can't work out the concentrations. Fear not, because all the volumes in this will cancel out. If they cancel out, you can just use them straight with moles. Now, how can I tell? It's because if you look here, let's write this as moles per decimeter cubes. I'm just gonna write N for moles and volume as volume. So N over V is your concentration, right? So you got N over V squared, and you've got N over V, and then you've got N over V times N over V squared. These would all cancel out. Therefore, the volumes are irrelevant. You can just use it in terms of moles. Actually, in fact, all of these units cancel out. Therefore, the moles of H2O squared are going to equal all the numbers put in. So it's going to be 0.452 squared times the concentration of the diol, which is 0.273, all divided by the concentration of the diester, which is 0.971, times Kc, which is, in this case, 0.161. Therefore, the moles of H2O squared equals, let's put those numbers in and see what we get. So 0.452 squared times 0.273, 0.971 times 0.161. That gives you 0.357. Therefore, the moles of H2O is the square root of that, which is going to be 0.597. Okay, so it says, this question is about isomers of the molecular formula C5H10O, and it says draw the skeletal formula of a branch chain aldehyde with molecular formula C5H10O that is optically active. Okay, so in order for an optical isomer to exist, you need to have a chiral carbon. So a chiral carbon means that you've got 4 different groups attached to it. So we need to come up with some sort of skeletal formula where we have a carbon atom with 4 different groups on it. So it's an aldehyde, so we're going to have a C double bond O, and it has to be at the end. So there's my C double bond O. And then what I might do is I might put a carbon in the middle here. So we've got a carbon with a methyl group on it like that, and that's branched. It's got a hydrogen here, it's got a carbon here, and then we can just slap on the rest there. So it's 1, 2, 3, 4, 5, which fits the formula C5H10O. And this middle carbon has 4 different groups. So it's chiral, therefore it has to have optical, what's the word? Optical activity. Describe how you distinguish between separate samples of the two enantiomers of the branched chain aldehyde C5H10O. So what you do is you use plain polarized light, and this rotates the plane of light in opposite directions. It says draw the E and Z forms of a structural isomer of C5H10O that shows both optical and geometric isomerism, also known as EZ isomerism. So we've got an EZ isomer, so we're going to have a C double bond C in the middle, and it needs to have optical isomerism as well. So we need a carbon with 4 different groups on. So what I'm going to do is I'm going to, first of all, I've got the base parts here. I'm just going to add a methyl group here, H3C, and an H here, and then an H here, and then try and weasel out something with the rest. So 1, 2, 3, that means we're left with 2 more carbons. So what I could have is I could have C, an H, CH3, and an OH. That way we have our chiral carbon here, and we've got a double bond, so there's the AZ isomerism. So now we obviously need to draw the other isomer. So that's the E isomer because they're on opposite sides. And now we need to draw the Z isomer. So that's CH3, CH3, sorry, CH, CH3, OH, H, and H. There you go. Okay, so isomer J is cyclic and has an ether functional group COC. Isomer J only has 3 peaks on its carbon-13 NMR spectrum. Draw 2 other cyclic isomers of C5H10 that have an ether functional group and only 3 peaks on their carbon-13 spectra. Right, okay, so we need to try and make something that is symmetrical as possible, to be honest. So, cyclic isomers. So what I'm going to try and do is I'm going to try and draw just a simple, some sort of, cyclic shape based on what it has. So obviously we've got 5 carbons, we've got an ether group here. So it's not really going to be a pentagon because we've got that ether group in the way. So an ether group here, got a C here. I'm going to draw, sorry, I'm going to do squeeze. We've got a C there, got another C there, another C there. So that's 1, 2, 3, 4, and then one that joins in there, 5. So there's 1. Now let's check, does it have 3 peaks in its spectrum? So 1, that's the same as that. 2, that's the same as that. And 3, so it's going to have 3 peaks, 3 carbon environments. So there's 1. Now what I'm going to do is I'm just going to take this and I'm going to take out one of the carbons from this shape and then just stick them on the ends. So I've got O here, and then I've got this here. Like that, so that's 1, 2, 3 carbons, 4, and 5. Let's see how many carbon environments we've got here. So now we need to look at the carbon environments we have. So we've got 1 here, and this one's the exact same, so those are both 1 peak. We've got 1 here, and then we've got 1 here, and 1 here, and they're the same as well. So that's 3 peaks overall. Okay, so this question is about spectroscopy. Compound K has the molecular formula C4H8O, and it shows the infrared spectrum of K. We can see right off the bat, what's that, 1,700-ish? We've got a big fat peak here, so it's probably going to be a carbonyl group because it's got a C double bond O, so it's that one. Compound L has the molecular formula C4H7NO, and it shows the infrared spectrum of L. L reacts with H2 in the presence of a nickel catalyst to give the compound M. Suggest 3 ways in which the infrared spectrum of M is different to that of L. Right. So it is C4H7NO. So we need to think about all of the different things that we know of that can react with H2. So the only thing that has nitrogen in that can react with H2 to give you something else is a nitrile. So we've probably got a nitrile group in this. And also if we look here, we probably identify it as well based on the peaks. So we've got a peak at about like 2,200-ish. So there's a peak, and that corresponds to C triple bond N. If you're reacting it with H2, we need to think about our synthetic pathway and what it makes. So if you react a nitrile with H2 in the presence of a catalyst, blah, 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 you make a primary amine. So you go from that to an NH2. So that peak will disappear. So peak at 2200 disappears. And now we're going from something with C triple bond N into something that has a an NH bond. So that means we're going to have a peak at 3300, to 3,500, whatever's in the data sheet. for NH appearing. And then we need to think about the third change. Well, the fingerprint region changes as well. Remember, this is unique to each each type of organic compound you have. So if we're going from one to another, then the fingerprint region is going to change regardless. Okay, so figure 7 shows the proton NMR spectrum of Q, which is the formula C3H7ClO. Cool. And they've given us chemical shifts and integration values for each peak. So the integration values, we can already work out the ratio. If you divide these both by 0.3, you get a ratio of 2 to 2 to 3. So in these questions, whenever you're doing them, the bulk of the work comes from showing your reasoning. Usually you'd get like 1 to 2 marks to actually work out the structure. So when you're doing these questions, just write out all the possible information that can lead to the pieces, and then you can try and aim for the structure. If you can't get the structure, at least the fact that you've written all of that stuff down helps. So we've got our integration ratio. I'm going to write integration in your exams, is 2 to 2 to 3. So this is going to be helpful to work out the bits and pieces that we need. So we've got a peak at 3.95. So where's that? It's a 3.95. So it's like around here, and it is a triplet. So if we look at our data sheet, what does that correlate to? 3.95 correlates to, so in the data sheet, it's going to be RCH2Cl or Br, right? So cool. This is the hydrogen that triggers that peak. Now, because it has an integration of 2, that means it's got to be CH2 and it's got to be a Cl. So we've got, this piece has to be CH2Cl. And because it's a triplet, the neighboring carbon has to have 2 hydrogen atoms because the n+1 rule. So it has to be next to a CH2, like that. So we've got piece 1. So in this, so what you would write down is you would write peak at 3.95 is, RCl, CH2 or CH2Cl, and it is a triplet, therefore next to a CH2. And then you would sketch what the little piece would be. So CH2, Cl, CH2. I should actually do CH2Cl like that. So that's the piece there. And if you do that, you can secure most of the marks. So as well as that integration ratio 2, therefore 2 H's on there. So that gives you that. You doing that gets most of the marks. I mean, you have to say all of this for 1 point at 3.65. So if we look at 3.65, it's a triplet. So whatever's next to it has to be a CH2, and it's an integration of 2. So integration 2. So let's have a look what this correlates to. So 3.65, according to the data sheet, is, we've already tackled the one with the Cl, so it's probably not going to be RCH2Cl. So the only one it could be is ROC, and then this H is one that triggers it. Now, because it has an integration of 2, it's going to be CH2. And because it is next to a CH2, that means the neighboring carbon has to have a CH2. So next to CH2. So what we now have is we've got 2 pieces. We've got CH2, CH2Cl. That's piece 1. We've got RO, CH2, CH2. Let's look at the last peak. So we've got a peak at 3.35, and that is a singlet. Therefore, there's no adjacent H's. Its integration is 3, so this is going to have 3 hydrogens on it. So now let's look at this, what this correlates to. So we've got a peak at 3.35. That's going to be R, O, C, and whatever. So it's got an integration of 3, so it's going to be CH3, and then the thing next to it has no hydrogens. So now we need to put together all the pieces we have. Doing this has secured us 4 out of the 5 marks. The last one in this question just comes from working out the structure is. So we just need to put all the pieces together until we figure it out. So this is probably going to be on one end. So we've got CH2, CH2, Cl on one end. This group, remember, is next to a CH2. So it's probably this CH2 it's next to. So we've got CH2 like this. Sorry, not CH2. This group, sorry, is probably going to correlate to this. So I'm going to have an O here like that. And then this is the CH3 next to an O. So it's probably going to be this. So that gives us 1, 2, 3. So it's 3 C's. There's 1 Cl. That's 3, 5. That's 3, 5, 7. Yeah, that works out. So there you go. If you just make sure you write all the sort of reasoning out like that. So always say what the peak is. So what you do is you always write the integration ratio out first. You should also say the number of hydrogen environments. I forgot that, sorry, but you've got 3 main environments here. And then you also need to describe each peak. So you need to say what it correlates to. Is it a triplet? And therefore, what's it next to? And its integration. So how many hydrogens they have. You need to say all of those parts for a mark or else you don't get them. So simply dumping out all of this information gets you most of them. So just make sure you do that. Right. So this question is about making a diester from cyclohexanol. So we've got cyclohexanol and we're making some sort of cyclic alkene. And then we're doing some other stuff. And now we've got 2 OH groups. And then we've got a nice old little ester going on here. Right. So state the type of reaction in step 1 and give the name of the reagent. So we're going from an alcohol to an alkene. So this is dehydration. And this is using concentrated H2SO4. So state the reagents needed and give equations for step 2 and 3 and show the structure of compound G in your equations. So let me just have a quick look. So we need to go from an alkene to something which allows us to then have OHs. So we need to think of all the reactions that alkenes can undergo. So alkenes, you can either you can add HX and you get a halogenoalkane, or you could add you could add like a di, so like Br2 for example, and you would end up with dibromoalkane. Or you can add H3PO4 and heat it with steam and you get an alcohol. It wouldn't be H3PO4 and alcohol because it would just be straight that way. So we need to think of an intermediate step. So we need to think, what can we do instead? What you can do is, if you think about your mental synthetic pathway, is you can add 2 BRs to this and you would end up with this. And then you've got essentially a halogenoalkane with 2 halogens on. So you could do nucleophilic substitution and swap these for OHs like that. And that's what they're getting at here. You're adding Br2. So this equation would be this. And then the third reagent is obviously you're using you're doing nucleophilic substitution. So you want a strong base. So you got NaOH. You got your Br like this. You're adding 2 NaOHs here. And that gives you this. So the OHs swap. And you get 2 NaBr, like so. Cyclohexane 1,2-diol reacts with ethane dioyl chloride. Give the name of this the mechanism for this reaction. Complete the mechanism to show the formation of 1 ester link in the first step of this reaction. Okay, so we've got an acyl chloride, and we need to think about what we're reacting it with. So in your big synthetic pathway, you need to think, okay, acyl chloride, what can I do with acyl chlorides? If I react an acyl chloride with an alcohol, they react vigorously to produce an ester. And the mechanism by which they do this is called nucleophilic addition elimination. So how this works is that both the chlorine and oxygen atoms, they pull electrons towards themselves. So this makes this carbon slightly positive, meaning it's susceptible to nucleophile attack. So the first thing that happens is that the C double bond O breaks and a pair of electrons are moved onto the oxygen like so, like that. Then what happens is a nucleophile attacks this slightly positive carbon. So we need to think about where the nucleophile is here. It's one of these OHs like that. So it comes along and it does this. So now we need to do the dastardly thing of drawing this thing grouped together. Okay, so what you end up with is you've got to draw bonds between all of these different things. So your carbon's here. Your carbon's now got it's got this, so this becomes an O minus with an extra pair of electrons like so. This COCl is intact, so it stays the same, COCl. Then there's a Cl here as well, so that Cl also stays intact for now. And then we're obviously joining it with this oxygen. So this oxygen's here, like so. It's still bound to that H there. And then it's bound to the rest of this compound here, like so. Like that, and OH. However, this is positive now because it's got one too many bonds. That nucleophile has bound here, and it's got one extra bond than it wants. So this bond has to break. So what happens is that this negative oxygen here, what it does is the lone pair of electrons from here reform the carbon double bond. So it wants to do this. Now, obviously, carbon can't have this many bonds. It can't have a double bond here and all of this stuff going on. So it has to boot one of the things off. So what it does is it kicks off the chlorine that it was bonded to in the acyl chloride. So this bond breaks like so, like that. And then obviously we're stuck here with this extra H as well. And we're stuck here with this O plus here as well. So what you need to do is you've got to break this bond here as well, like that. And then this leaves behind an acyl chloride derivative. So you don't need to draw the rest of it. You just need to draw the mechanism. This is absolutely awful. But basically, it's taking the principles of a normal acyl chloride reaction and understanding that this acts as the nucleophile. All the reactions involving acyl chlorides work in this exact same mechanism. You just need to change what the mechanism is. So, for example, in water, the nucleophile is the oxygen and the H2O. If it's an alcohol, it's the OH group, as it is in this case. This is a diol. It's two alcohols. So it's the O in this case. It could be ammonia, NH3, or it could be an amine. So like CH3, NH2. That's the lone pair there. So it's just important to recognize that this is what they were trying to get at. Is that that's the nucleophile, and you have to draw this whole ass mechanism doing that. It's a bit clapped, but it is what it is. Suggest why chemists usually aim to design production methods with fewer steps and with a high percentage atom economy. Well, it's because first of all, I mean, you have fewer steps. It's important because you're using less energy, so less energy used. Imagine having to so for example, if I wanted to go from alkene to an alcohol, I could just use H3PO4 catalyst and steam and heat it. Or what I could do is I convert it to an halogenoalkane and then I convert it to an alcohol. That's going to require me to reflux it and then reflux it again and all these other steps. I could have done it in one step rather than two, so there's less energy wasted. The other thing about the high atom economy is that you're making less waste. This question is about the ozone layer in the upper atmosphere. Suggest why the ozone layer is beneficial for living organisms. It absorbs harmful UV radiation or ultraviolet radiation. Right. Suggest how chlorofluorocarbons form chlorine atoms in the upper atmosphere. So what happens is you in your chlorofluorocarbons, what happens is so CCl, this bond breaks, and then it makes a chlorine radical, and it goes and does all kinds of God knows what. So basically, what you're trying to say is that the CCl bond breaks. And for brownie points, you can say it breaks homolytically, meaning that each one gets an electron. Heterolytically means that one gets both the electrons in the covalent pair. Right. Give equations to show how chlorine atoms catalyze the decomposition of ozone. So this is just one of them ones you gotta know. So chlorine radical attacks an ozone, and this forms ClO radical plus O2. This ClO radical then goes and attacks another ozone, and that forms a Cl radical plus 2O2. And you can see the cycle repeats because it then goes and attacks another one, and it's just this constant cycle. Hydrochlorofluorocarbons, HCFCs, have been used in place of chlorofluorocarbons. In the mechanism to make an HCFC from a fluoroalkane, two incomplete steps are shown. Complete each step in the mechanism and give the name of the type of the step shown in both of these equations. Okay, so in this first step, we've got some mystery compound that, this carbon atom loses one atom, and this takes the atom and binds with a chlorine. So we know for a start that this has to be a chlorine radical that's doing this first attack. We now need to identify what the other missing thing is. It's got to be hydrogen, because the hydrogen bonds with the chlorine radical giving you HCl. So the original thing must have been CH2F2, like so. And then this CHF2 radical attacks the Cl2, so it's going to form a CHClF2 plus Cl radical, and this step is known as propagation in free radical substitution. This question is about the rates of reaction. Iodine and propanone react together in an acid-catalyzed reaction. A student completed a series of experiments to determine the order of reaction with respect to iodine. The method is to transfer 25 centimeters cubed of 1 mole per decimeter cubed propanone to a conical flask, add 10 centimeters cubed of 1 mole per decimeter cubed HCl, add 25 centimeters cubed 5 times 10 to the minus 3 mole per decimeter cubed I2, and start a timer. At intervals of 1 minute, remove a 1 centimeter cube sample from the mixture and add each sample to a separate beaker containing an excess of NaHCO3. Titrate the contents of each beaker with a standard solution of sodium thiosulfate and record the volume of sodium thiosulfate used. So suggest why 1 centimeter cube portions of the reaction mixture are added to an excess of NaHCO3 solution. So what we're doing is we're reacting an acid. So it's an acid catalyzed reaction. So this reaction is being propagated by an acid. So if we're taking a mixture of this stuff out, we don't want it to keep doing the reaction while we're trying to measure all of this stuff, because if it does that, it's going to affect our results. It's going to make things higher or lower, blah, blah, blah. So the reason we add an excess of this is to neutralize the acid catalyst and stop the reaction. Suggest why the order of this reaction with respect to propanone can be ignored in this experiment. If we look at how many moles of propanone we have, oh my god, we have 25 over 1,000 times 1, which is 0.025 moles. If we look at iodine, we've got 5 times 10 to the minus 3 times 25 times 10 to the minus 3. We've got 1.25 times 10 to the minus 4. So how many times more of that do we have? We have 200 times more propanone than there is I2. There's so much propanone that you can assume that the propanone's concentration is near constant. So it's not, it's not limiting the reaction. So it's not going to cause any problems with rate. So the concentration of propanone is almost constant because there's so much of it there. Because there is a much larger amount of propanone compared to iodine. Okay, so the volume of sodium thiosulfate, blah, 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 proportional, blah, 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 plot a graph, whatever. Yeah, fine. Plot the graph. You can do that. So it says, explain how the graph shows that the reaction is zero order with respect to iodine in the reaction between propanone and iodine. So the graph should have just been a straight line like this. Yeah, I'm not going to draw it because, come on. So the reason we know this is the case is because as time goes on, the volume of thiosulfate dropping at each point is effectively the same. It's a straight line. So whenever you have a straight line, it means the gradient's constant, and we've got volume against time, so the rate of this is constant. If it were to be first, second order, blah, 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 it would be a curve and it would change. But you can see the rate at which the volume of sodium thiosulfate drops is the same throughout. It's not changing. If it wasn't dropping, the line would be horizontal, so nothing would be happening. If it was infinitely dropping, it would be going like this, obviously. And because it's going this way, the steepness is the same, so it's constant throughout. So in this case, the gradient is constant. So the rate of reaction doesn't change as iodine's used up. Because obviously as the reaction goes on, iodine drops. So if it were to have an effect, then this line would be a curve. Because when you have a curve, it means the gradient's changing. So for those that don't really have as much maths knowledge, or for those that, do and just don't get it, the gradient is the steepness of a line. So here it's steep, here it's not so steep, and here it's barely steep at all. The gradient is changing. Whereas here it's consistent. It's the same steepness throughout. So if the steepness is changing, that means that the rate is changing in this case. So iodine does play a role. Because the rate is completely the same throughout, no matter how little iodine becomes, you can assume that iodine just has no role on it, because as the reaction goes on, iodine drops, but it's not affecting the rate, it's not affecting the steepness. Okay, so the Arrhenius equation can be written as ln k equals minus EA over RT plus ln A, and it shows a graph for this, blah, blah, blah. Use the figure to calculate a value for the activation energy, and they've given you this. Right, so the Arrhenius equation, everyone panics about. Whenever you've got a graph, right, you always need to think of it as y equals mx plus c. So what this means is y on your what's on your y-axis, x, what's on your x-axis, m is your gradient, so that's gradient, and that's what is multiplied to x, and then c is your y-intercept. Right? Okay, so they've given us this equation, ln k equals negative EA over RT plus ln A. And they've given us a graph of ln k against 1 over t. So in our exam, in this question here, so in our question, what's on the y-axis is ln k, right? What's on the x-axis is going to be 1 over t. So the y-intercept is whatever's here. So there's plus c, so it's going to be plus ln A, so it's going to be ln A. And then our gradient, m, is whatever is multiplied onto 1 over t. So to get from 1 over t to minus EA over RT, you have to times it by minus EA over R. Just because minus EA over R times 1 over T gives you minus EA over RT. So that's how you derive this part. So you could either remember it, but obviously if they change the axes up, then you're kind of screwed. So for example, if they give you a Gibbs free energy thing, right? Delta G equals delta H minus T delta S, which they do love asking a lot, right? They might give you a graph of delta G against T, like so. So what you always do is do the same thing. So it has to, every straight line follows y equals mx plus c. List out all your variables. So y in this case is delta G, that's on the y-axis. X is going to be whatever's on the x-axis, which is T. M is whatever's stuck to the x. So if you look at the equation, what's multiplied onto it is negative delta S. So negative delta S. And C is your y-intercept. That's basically everything left in the equation, which is delta H. And that's how you can use this to work out the rest, because you know the gradient is M. So in this example here, our gradient, M, equals negative EA over R. So what you do is you pick 2 points and you work out the gradient. So what you do is you draw the y step over the x step. You do y2 minus y1 over x2 minus x1. You always do this way's coordinates first. So a lot of people, what they'll do is they'll subtract this y coordinate by this this y coordinate by this one. That's incorrect. You need to do this y coordinate by this one. Because as you go this way, you're doing your y value gets higher. Like as in your y, this is your first y point, that's your second, that's your third. So if I'm working the gradient using this point and this point, I need to use this y coordinate minus this y coordinate over this x coordinate minus this x coordinate. So if you do that, then you should end up with some number. I'm just going to steal what the mark scheme says. So your gradient is going to be minus 21731, right? So this is negative EA over R. So we need to times this by R. So minus 21731 times 8.31 equals 180,583. Oh, sorry, minus that. But this is minus EA and they want EA, so it's going to be 180,583. But they also want it in kilojoules per mole. This only works in joules, so it's going to be 181 or like 18.5, blah, blah, blah. So just that's how you do that last one. Thank you very much for watching. I hope that's been helpful. Please like and subscribe, share all of that kind of stuff. Help us grow and help us get out there, man.